Hello, I'm Mikhail, and I'm presenting this paper on compositional quantum control flow with efficient compilation in Qunity, which was done in collaboration with Finn, Leah, and Robert. So the most prominent model of quantum computation that we typically see is this circuit model, and most ways of thinking about how to program quantum computers rely on this idea that we have some classical computer that maybe constructs a quantum circuit, sends it to a quantum computer, which then runs it, measures the qubits and NAND, and sends the result back, right? And we can continue doing this and to represent some sort of quantum algorithm. However, this does not really feel like high-level programming, right? When we write classical programs, we typically don't represent them in terms of just logical gates, which is the equivalent of quantum gates. So the question we were trying to answer is, can we write quantum programs in a way that is high level, on a higher level of abstraction than the circuit model? And this is what the Qunity language attempts to do. So the main goal of Qunity is to try to take certain existing programming constructs from classical computing and try to generalize them in a natural way to quantum ones. So for example, we have notions of control flow, pattern matching, error handling, and some complex data structures that we want to have quantum versions of. So this was originally proposed in 2023 as kind of theoretical construction, and in this work we propose some extensions to the control flow features in Qunity to improve its expressivity, and we implement the first compiler that converts Qunity into low-level quantum circuits in OpenQASM. And we design various optimizations for this compilation process. So first, I'd like to start with this example of a famous quantum algorithm called Grover's algorithm. So the problem is we're given a function that takes in n bits and it outputs 1 bit, and we want to find an input to this function such that f outputs 1. So the basic idea of how Grover's algorithm works, right, is that we start in an equal superposition of all the inputs, and we try to repeatedly apply certain reflections of the quantum state using our function to rotate the quantum state around until it eventually gets closer to the correct value, right? It turns out this gives a quadratic speed up. So, but how do we actually implement this on a quantum computer as a circuit, right? So first of all, our function f could be any function on n bits, and it might not be reversible. In most cases, it's not, right? But when we build quantum circuits, they are unitary and they have to be reversible. So first thing we have to do is we have to somehow encode our function into a quantum circuit. So the typical way of doing it is something like this, where we add in an extra ancillary qubit, and the circuit has to basically flip it depending on what the output of f is. So once we have that, then using a typical framework like Qiskit, where we are specifying how to construct the circuit, it will look something like this. So somehow this composes these circuits that will represent these reflections of the quantum state. But this doesn't really feel like something that's high level, and it's not entirely obvious from first glance that this corresponds to that picture of rotating the states and like how we think of the algorithm. So also, like, this idea that we have this function f, we have to first convert it into this quantum oracle that we then put into the circuit. But ideally, what we really want is we want to just write f as a function normally without worrying how it integrates with everything else, and then just be able to simply plug it in, right? So we want to use it as a subroutine without needing to worry about how to adapt it to this algorithm. And then another thing, hypothetically, we might want to even implement f with a quantum algorithm. Maybe it's some really complicated computation that we need to run a quantum computer on to find what it is, right? And another thing is, like, we have, this is running on functions from n bits to 1 bit, but what if we have maybe some complicated data structure that we really don't want to bother trying to figure out how to encode it into bits, right? So this is all the things that we want to happen in a high-level language, and this is what happens in Qunity. So here, this is our new syntax for the Qunity language, and this is what a Grover iteration looks like in Qunity. So first of all, you can see that it works for an arbitrary data type in Qunity, provided that we give it how to generate the equal superposition of a data type. And we can take in basically any function that accepts this data type and outputs a bit. And so then here it's very clear what this does. We have this control condition on the output of f, and we have this pattern matching. In this case, very simple. If it's 1, we apply a phase. And then after that, we just reflected about the equal superposition. So the key thing that makes this work is this control construct. So in Qunity, the idea is that we allow to have these arbitrary quantum subroutines that we can condition on. However, for this to actually work and be physically realizable, the Qunity type system does have to impose a lot of restrictions on all the other parts of it. So this is the typing rule for control in Qunity, and kind of the main biggest constraints here are that, first of all, the patterns themselves that we're matching against have to be classical, and we have this erasure condition on the branches on the right-hand side of this block. And so this is needed because if you don't have these constraints, the semantics of this as a quantum operation might not be something physically meaningful. You might have something like increases the norm of a quantum state, which we don't want. But we might want to try to avoid these constraints, potentially trading off some of the capabilities of control, thus so that we have more flexibility on the kinds of quantum control flow we can do. And so this is what we did in the work, and we augmented Qunity with 2 additional control flow features. Here are called match and p-match. And so the idea is that they offer different trade-offs with the capabilities of control. So for example, match is designed to work just kind of as a match statement in classical languages. So it has very minimal restrictions on how you define the control flow structure. But unlike control, it itself does not have pure or reversible semantics. And then the other one is p-match, which is a form of kind of symmetric pattern matching between orthogonal sets of expressions. And here, unlike in control, we can have an arbitrary basis for all the patterns in the branches. But again, you don't have the subroutine capability. So here's just an example of how you might use match. So just to implement the AND gate, which is really simple and like the way you would do that just in classical programming. But the cool thing about this is you can easily just plug it into a quantum algorithm. So for instance, you can just use this and take it and put it as the F for Grover's algorithm. And it will work because the compiler will automatically figure out the purification and make this into that quantum circuit. And then here's an example of where you might use p-match. So we have this data type, which is maybe type that has 3 different values, and we want to prepare an equal superposition of this. So this is how you would do that with this p-match construct. But then if you were to use only control originally, you have to do this kind of ugly construction because of this erasure restriction. So essentially we'd have to do on computation manually, which we really want to try to avoid because kind of the goal in Qunity is to automate the process of on computation. Okay, so another thing you've been seeing through all these examples is the syntax this is written is really kind of a meta-programming layer above the core Qunity language. So in the actual language, we don't really have a notion of recursion or higher order functions because these things are notoriously difficult to extend in a meaningful way to quantum computation. There's some work that does that, but it doesn't really fit into the framework that we're doing with Qunity. So, but we do have these on the layer kind of above Qunity that gets preprocessed and converted into main language. So you can easily do things like, write the actual Gerber that combines several iterations, starting with the equal superposition. Okay, so this is the process we have for compiling Qunity. We start with this high-level program. After preprocessing, we just have the Qunity core language. And I guess the interesting thing is that then we have all the typing rules in our language. So here's an example of just how the pair is typed into the product type of T0 and T1. And then that is converted into this intermediate representation. And the idea is that these are kind of these high-level circuits where instead of the wires representing individual qubits, they correspond to Qunity's data types or context. And so here, for example, you can have some quantum variables that are present in both E0 and E1, and that corresponds to just sharing them along the classical basis and plugging it into the corresponding circuits. However, if and that's then compiled down to low-level circuits. But if you just naively do this implementation, if you just try to run something very simple, like this is an example of how you might do a CNOT gate, it compiles to something ridiculous initially, right? So we have to kind of try to figure out how to optimize this compilation process. So we'll look at this procedure and all the different stages of it. And on each stage, we tried changing something in the process to optimize it. So the first thing you can do is, of course, because like in the conversion to low-level circuits, you can just do some sort of standard post-processing techniques just for optimizing the circuits themselves. But this by itself is not really enough, and we have to do something on the previous stages. So here, for example, when converting from the intermediate representation, some things we did is figure out how to recycle qubits when it's possible, and also how to better construct circuits for the direct sum, which are essential for performing the pattern matching in the control flow constructs and representing different data types. And on a higher level, we also have ways to more efficiently construct the intermediate representation circuits themselves, using different ways to represent how to compile these orthogonal expressions in the pattern matching blocks, for example, and to efficiently transform it with the different types. So this is just an example of we ran this on various different benchmarks. And as you can see, there's a very significant improvement in the optimized compiler compared to our initial implementation. In many cases, it gets pretty close to the manual low-level circuit implementation. But in some cases, for more complicated algorithms, there's still a lot of room for improvement. To conclude, we have constructed the first Qunity compiler. We expanded the language itself with more enhanced control flow constructs, and we figured out several techniques to optimize the compilation. So in future work, something we could also do is try to compile to a different target and potentially include hybrid classical quantum programs in our final language. So thank you. This is the paper and the code. And thank you. Are there any questions?
Thank you. Questions, please.
Mm-hmm.
On one of the previous slides regarding optimizations, you mentioned that you do qubit recycling.
Yeah.
Qunity also supports errors. Have you investigated how qubit recycling affects errors, and what happens if you recycle a qubit when you're in an error state?
Yeah, so the idea is that we represent errors by having certain qubits for signaling them, right? So there are certain flag qubits that if they're in a one state, that represents that an error occurred. And so we can only recycle. So we can measure a qubit, If it's not inside a subroutine, that is an error, and after that we can recycle it. Or also, if the type checker determines statically that a certain program is error-free, then we can just immediately know that this error qubit can just be immediately recycled.
Thank you.
Thank you. We have to stop here. Sorry.